Hello everyone. Today I'm going to go through the example of solving the support reaction for an indeterminate beam using slope deflection equation. So there are two methods of solving an indeterminate beam, and by indeterminate beam means that your your reaction support reaction is greater than the number of equilibrium equation. So if the number of support reactions you have is greater than your number of equilibrium equations, then in that case it called as indeterminate beam, which means that it's not able to calculate all the unknown reaction using just the equilibrium equation. So there are two methods. One is slope deflection equation, or we call it displacement method, and the other is force method. So here I'm going to go through the slope deflection. And for slope deflection, the first thing that I would like to talk about is a sign convention. This is very important because many different authors in the textbook, or even in your classroom, or even in you'll see all the resources, they have a different sign convention. I mean, by different we mean that positive, negative, the meaning of positive and negative can be different. So in my case, in this video, I'm going to make it clear that our sign convention is if the member n or the n rotation or a chord rotations, they are positive when counterclockwise. That means if you apply a moment on in counterclockwise at a joint, and we'll take that as a positive, and if it is clockwise at the joint, we'll take as a negative value. And regarding the chord rotation, this is mainly you'll see in a settlement. So in this example, I'm not going to do any settlement in the support. I'm going to do in the next video, where I'm going to show you if there's a settlement in the support, how do you consider whether it's positive or negative settlement. Okay, so what are the steps in using the slope deflection equation? First, you need to find the degree of freedom. By degree of freedom means how many variables you're going to have in your equation. So the number of degree of freedom will tell you how to do that. Then once you have the degree of freedom, we'll calculate the fixed and moment due to external loading. You'll see that in the equation of slope deflection, there is also the contribution of the external loading to the moment at the joint. So we already have this table for finding fixed and moment formula. These are all the formula for different loading. For example, if both n are fixed and there's a UDL or uniformly distributed load, and this will be the fixed end moment formula at each joint. And similarly, if one end is fixed and the other one is a pin or a roller, and you have a load, and so this will be your uh, fixed end formula for the fixed end, and there will be moment it will be equal to 0 if it is a roller at the other end. So we are going to use this table. And also also in your FA exam, and I believe in even in your classroom, in your class exam also, most of the loading will be um, given to you, like it'll be more familiarized with this kind of loading. Anything complicated might not be it's not worth it, because if there's a complicated building, I mean complicated loading, you'll be using software. So in a real project, actually you'll be using software, so you don't have to stress yourself over the complicated loading, unless the objective of the class is for you to find the fixed and moment formula only. Okay, but if you're going to use a slope deflection equation, generally the loading will be common as given in that uh, sheet. And once you have the fixed end moment, you're going to use a slope deflection equation, arranging all the putting all the known value, and then find out what are the unknown value, and then you will use equilibrium equation to find the unknown reaction. Please make sure that in your slope deflection equation, your equilibrium equation will be um, your main equation, whereas in your force method, your compatibility equation will be your main equation, uh, and then after that you'll be using equilibrium equation to find all the unknown forces. But in slope deflection equation, you must meet the equilibrium equation. So let's Let's start with our example. You have here the pin joint at A, roller at B, and roller at C. And you can see here that if I find the degree of indeterminacy, if I draw all the reaction, this is, remember that our axis is, this is x, this is y, so this will be ay, and this will be ax, and this will be by, and this will be cy. So you'll see that there are one uh, 1, 2, 3, 4. There are four unknown reaction, and there is just one beam. So we have three equilibrium equations. So degree of indeterminacy will be 1. 4, 1, 2, 3, 4 minus 3 is equal to 1. So we know that it's going to be indeterminate uh, beam. So the first thing is to find what is your degree of freedom. And what is degree of freedom? We are going to look at each joint. So each joint, at A joint, we don't have it cannot we it it's not moving up or down, neither is moving sideways, but it can rotate freely. So we have 1 degree of freedom at A. So we have theta A as your degree of freedom. And then we'll look at roller support. Roller support, you cannot move up, and because in your slope deflection equation the assumption is there's no actual deformation, because there's no actual deformation, then we expect that this roll will not move at all, even though we know that roller support can move sideways. But if there's no actual deformation, then this beam cannot stretch at all. Okay. So because of that, the only rotation that it can have is uh, the only degree of freedom it can have is a rotation. So you have here theta uh, B. And then similarly for at joint C, remember that degree of freedom is always at a joint. So at joint C, you all, again, no actual deformation. So your theta C will be your degree of freedom. So we have 3 degree of freedom, which is theta A, theta B, and theta C. And these are the variable that you're going to see in your slope deflection equation. Okay, so that is all about degree of freedom for a beam. And then next one is number B, is to find the fixed end moment due to external loading. And so we are going to divide part by part, because we are doing a slope deflection, and that means it's a member between two joints. So we are going to use for a span AB. We are looking for the span AB, and you'll see that A is pin, but this is called as your internal roller, and internal roller will be equivalent to fixed condition. So because it is an internal roller, it's equivalent to fixed condition. Why? Because you'll see that when you draw a bending moment of any internal roller, moment will not be equal to 0. It will always carry some moment. So because of that, the internal roller or internal pin will be considered as a fixed uh, connection. So in that case, you'll have for span AB, you have a pin, and also you'll have a fix. So A, B, and you'll have a uniform distributed load of 10 kilonewton per meter. And you'll see that this will be my n moment MAB, which is fixed moment at A uh, in a beam AB, and this will be, I will say that not MAB, because that is total moment. You'll call as fixed end moment of AB, and then this will draw. We always follow the sign convention of positive. So this will be FEM uh, for at a joint B in a beam AB. So this is called as fixed end moment at joint A in a beam AB, and this is called as and for this one it's called as fixed moment at joint B in a beam AB. So you see that the one A and B come first, which means that the joint, we are talking about joint at A, and here we are talking about joint at B. Okay, so for this we are going to see the using the table sheets, and you'll see that this is the one that we will need because it has fixed and it has a pin. And the we know that there will be no fixed end moment at pin, so 0. So now the only equation will be WL square over 8. And if you see in this formula, all this fixed end moment formula, you'll see that the way that they have derived the formula is this is counterclockwise, this is clockwise. So which means that if I switch this will be clockwise. So uh, so that means this is clockwise, and our sign convention is counterclockwise. So for FEM AB, because it's a pin, is going to be 0, and FEM BA, because it's going to be uh, clockwise, and our sign convention is counterclockwise. So we'll have negative WL square over 8. Okay, so please remember that the positive means this part is going to be a positive because it is counterclockwise, and this part, it would have been positive, it is counterclockwise, but the actual sheet that they use is going to be a clockwise. So if it is a clockwise, that means your value should be negative. Okay, so please keep that in mind, why it is negative in BA. And if you put this equal to minus 10, and your meter, this is 6 meter, 6 square divided by 8, you'll get this as 45 kilonewton meter. So these are all your fixed end moment for the span EB. And now we'll take the span BC, and for span BC, again, B is internal roller, so it's going to be a fixed, and then C is going to be a roller, and we have all the load, which is 10 kilonewton per meter, and this will be 6 meter. And once you have that, now you can find your fixed end moment for BC. Remember that this is always counterclockwise, but this will be equal to but this will be equal oops but this will be equal to 0 because there's no moment at the external roller support. So the FEM CB will be equal to 0. What about uh, fixed end moment at BC? Is going to be, because you can see from here that this value is WL squared over 8, and it is counterclockwise. And if it is counterclockwise, then that means it'll be positive, and that will be 45 kilonewton meter. Okay, so that's how we derive all the fixed end moment for each span, because remember that the joint has to be for a whole member, and there's going to be two joints, so that's why you have to divide into two span AB and span BC, because that's where we have the support condition. We have support condition A, support condition B, and support condition C. So we have span AB and we have span BC. Okay, so that's all about the fixed end moment. Once you have the fixed end moment, now the third one is to use the slope deflection equation. And for this, we are just going to write the formula. MAB is equal to 2EI over L twice theta A plus theta B minus 6EI over L square delta, and plus FEM fixed end moment for AB. And we are going to put all the value equal to 0, the one that we don't know because there's no settlement, is equal to 0. And FEM over AB, it's an external pin support, so it's going to be 0. So your L will be 6 meter, so it will be 2 EI over 6 2 theta A plus theta B. And we know that moment, the actual moment at A is going to be 0, total moment at AB, because this is a pin, because moment at A in a span AB or in a beam AB is a pin joint at A, and pin will not take any moment, so we have a equal to 0. So finally we'll say that this is equal to 0. So you will find that your theta A will be equal to minus 0.5 theta B. Or sometimes it's easy to use EI theta A. So if you don't remove the EI, so it's going to be 0.5 EI theta B. Sometimes it's easy to use EI theta because you'll see that when we use the when you substitute the equation, we don't have to substitute for theta A, we'll just substitute for EI theta A. Okay, so that's all the moment about A for beam AB. And now moment about B for a beam AB will be equal to 2 EI over L. This is how it's helpful to remember. It's 2 theta B. So just look at what is the first letter is. If it's A, so we're going to be 2 theta A. If it's B, then it will be 2 theta B plus theta A minus 6 EI L square delta plus fixed M moment about BA. And fixed end moment about BA, we already calculated that is going to be minus 45, and this will be 0, and this will be 6 meter. And now if we put it together, you'll have 2, you'll have 4 EI theta B plus 2 EI theta A, and then minus 45. And you'll see that this EI theta A is going to be 0.5 EI theta B. So finally we can find that will be minus 1, so 3 EI theta B this is divided by 6, so it will be 6 minus 45. So you'll find that this is going to be 0.5 EI theta B minus 45. Okay, so that is the total moment at joint B in a beam AB. And now we'll do for the next one, which is your MBC will be 2 EI over L 2 theta B plus theta C minus 6 EI L square delta plus FEM BC. So we know that this is going to be 0, this is going to be 45. So finally we can, and this will be 6 meter. So finally we'll put that 2 EI over 6 theta 4 EI theta B plus 2 EI theta C over 6 and then plus 45. And then we cannot replace the theta C right now because we don't know what is the relationship. So we're going to write MCB is equal to 2 EI over L 2 theta C plus theta B minus 6 EI over L square delta plus FEM CB, and this will be equal to 0 because it's an external roller. Because it's external roller, we know that it cannot take any moment, and this is internal roller. Okay, so because this is an external roller, so it cannot take any moment, so moment will be equal to 0, and now we can put all this equal to 0, this also will be equal to 0. So finally you can write that 2ei theta c will be equal to minus ei theta p. So you can find that ei theta c will be equal to minus 0.5 ei theta p. And so if you finally replace this value here with minus 0.5 ei theta b, you'll find that this will be equal to 3 over 6 ei theta b plus 45, and this will be 0.5 ei theta b plus 45. So I'll write this as your equation number. I'll write this as equation number 1. This is equation number 2. This is equation number 3, and equation number 4. So that's how we use all the deflection equation to generate all the final equation. Okay, so that will be the third steps, and fourth step is using equilibrium equation. Fourth is equilibrium equations. So for this, we're going to draw the free body diagram because this is very important. Okay, so for free body diagram, we're going to draw a beam AB, and we know that it has a UDL of 10 kilonewton per meter, and we're going to draw a moment, total moment for AB. This will be MAB, and remember that moment at the joint will always take the total moment at the joint will always be counterclockwise. It will be total moment MAB, and then after that we take a small cut section because that's where the roller support is, the internal roller support BY. So if we draw all the shear force here, we'll call it this VAB, and this is VBA, and you'll see that because we cut the section at just at the B, that means the free body diagram has to be in equilibrium. So this will be your VBA, and then we take another beam. It's a BC, and it has a uniformly distributed load of 10 kilonewton per meter, and this will be VBC, and this will be VCB, and this will be MCB, and this will be MBC, and finally we have must maintain equilibrium at joint B, and because MBC is counterclockwise for a beam AB, so at this joint we'll have MBC, which is clockwise, and for this joint also we'll have clockwise MBA. So these are all your free body diagram, which is very important in your slope deflection. And so from this slope deflection, you now you can finally see that your AY will be equal to VAB, and then your MA will be equal to MAB, because those are the in connection. Similarly, you can say CY is equal to V. I'm going to write over here so that it's easy to remember. CY is equal to VCB, and your MC will be equal to MCB, And then here you can see that your by will be equal to VBA plus VBC. Remember equilibrium. So VBA, VBC are acting downward. So they must be equal to your total reaction By. And then you'll see that MBA plus MBC must be equal to 0. Okay, so at this joint, we know that we said that internal moment of our internal roller, the moment of internal roller will take some moment, but here we are just taking only one joint. Okay, so we'll just fictitiously or arbitrary, we are taking out that point and we put all the load and we have all this moment MBA and MBC and MBA. So if we take the equilibrium of moment at B should be equal to 0, so you'll see that the MBA plus MBC must be equal to 0. Okay, so the total moment must be equal to 0, but you know that this MBA and MBC will not be equal to 0. Okay, so these are all the equations that we need. Now we can use one of these equations to solve for all our unknown. So for the first one, we'll use a joint B, and we're going to use this equation MBA plus MBC, because we know the equation for MBA and MBC, and that will be 0.5 EI theta B minus 45 plus 0.5 EI theta B plus 45 equal to 0. So this will cancel each other. So finally, EI theta B must be equal to 0. So we get the final equation for EI theta B. And now we can find what is our MBA. And our MBA will be minus 45 kilonewton meter, and then MBC will be 45 kilonewton meter. If you ask how did we know this, you can go back to that equation that we have derived for equation AC. From equation MBA, it is 0.5 EI minus 45. So if EIB, this will be equal to 0, so it has to be equal to minus 45. And similarly for MBC, you'll see that MBC, if this is equal to 0, so you have only 45. Okay, so that's how you get minus 45 and plus 45. And now what do we do knowing all the moment? Now using knowing all the moment, we can finally solve for the case for this case, because we know this, we know this. Okay, so you can also write here just for your sake, at AB is equal to 0 and MCB is equal to 0. So finally, we'll take span AB. We'll just take only this section AB, and if we take moment summation of all the moment equal to 0 at A, so this is a point A. We are taking at a point A. This is your A. So at point A, you'll see that VBA into, this is 6 meter, this is 6 meter, VBA into 6 counterclockwise positive plus MBA again counterclockwise positive, and then we have minus 10 into 6 into 6 over 2, and this is clockwise, so negative, and then we have plus MAB, again this is counterclockwise, and this must be equal to 0. And from here we know that this is 0 and this is minus 45, and if we do the calculation, you'll get VBA is equal to so that will be equal to minus 45 minus 10 into 6 into 3 divided by 6, you'll get 37.5. So this will be 37.5 kilonewton. And because it's positive, that means it agree with our assumed direction. Okay, so that is VBA. And now if we take summation of all the y equal to 0, will be VAB plus minus 10 into 6 plus VBA is equal to 0. Finally, you can find VBA is equal to, if you put VAB, VBA is 37.5. So that will be 10 into 6, my 37.5, and that will be 22.5. So VBA will be 22.5 kilonewton, and this will be again positive, so which means that is agree with your equation. And once you have that, now we'll go for span BC, and now we are fixing on this span BC, and we are going to take summation of MC is equal to 0, so we'll have minus VBC into 6, again this is clockwise, plus MBC, which is counterclockwise, plus 10 into 6 into 6 over 2, which again counterclockwise, plus MCB equal to 0. And MCB is 0 and MBC is 45. So finally we can calculate that our VBC will be equal to 37.5. And now we take a summation of force along y direction, VBC plus minus 10 into 6 plus VCB equal to 0. So from here you'll find VCB, because we already find this is 37.5, it'll be equal to 22.5 kilonewton. So now we have all the equation given to you. So finally we can just fill up this equation. So this will be equal to AY will be VAB. VAB is sorry, is going to be, this is VAB. VAB will be 22.5 and MAB is 0, MCB is 0, CY is your CY is VCB. VCB will be 22.5 kilonewton, and then MBA, we all define MBA, and BY will be summation of VBA and VBC. So VBA will be 37.5, and then VBC is 37.5. So finally you'll find that will be 37.5 to 275. Okay, so there you have all your support reaction. Okay, so that's how we calculate all the unknown support reaction for the indeterminate beam. What was the question asked? Draw the SFD and BMD. Okay, and you'll see that because there's no settlement, so we don't even have to use EI at all in the equation. If there's settlement, you'll see that the moment will be changes because of the settlement. Okay, so let's draw the, finally we can, after doing all the work, we can finally draw the shear force diagram. Okay, so now for the shear force diagram, we're going to put all the load that we know. This is 10 kilonewton per meter, and this is AY, which is 22.5, CY is 22.5, and Py is 75 kilonewton, 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 and then um, we have the moment, uh, MPa. What do we have? Moment MPa. So we have a moment MPa, that is MPa is MPa is minus 45, so it has to be clockwise. So minus 45, so that means has to be clockwise. And then we have a moment MBC, which is 45. Okay, so how do we draw the shear force now? For shear force, um, this is positive, so it must go up. And how high? It's 22.5. And you can see that the direction also is upward, so that's why we know it has to go upward. And then we know that uh, this is a uniformly distributed load. If it's a uniformly distributed load, that means it has to go a slope. There'll be a slope of one linear, and at this point we know that VBA is 37.5, so it's going to be 37.5 kilonewton. And we know that there is a sudden load, so that means there must be a sudden jump, and that sudden jump will be 37.5 for VBC. And the only one thing to know is the summation of all the forces has to be equal to 7 kilonewton. And then we have, again, the slope has to be downward again, and then it has to go back to 0, and there's 22.5. Okay, so one thing that I tell the students when they draw the shear force diagram, always look at the direction of the force. So you'll see that this direction is upward, so always start from left to right, start upward. And then because you have a UDL, so it has to go a slope, linear slope of 1 degree, and VBA is 35, and then this is going up, so it has to go up such that the total is 75, and then it go down again with a slope 1 degree, and then you'll see that this going up, this also go up and come back to the zero line. Okay, so this is your zero line. So if in your shear force diagram, if you start from zero line and it come back to zero line, that means your shear force diagram is correct. And this is positive, this is negative, this is positive, this is negative. And for drawing the shear force diagram, this will be 0, this will be 0, and you'll see that uh, what does this, if you take out this beam, what does this moment do to the beam? It created a hugging. Okay, so this one will create a hugging, and this one has to be, because it's positive, so it has to be counterclockwise. Okay, so remember that this is negative, so that means we have to change to clockwise. This is positive, that means this has to be counterclockwise. Okay, so and then you'll see that what it does for this beam, this moment created a hogging, and you'll see the beam BC, this moment created again a hogging. Okay, so both will be hogging. So if both will be hogging, that means this point will be minus 45. And so because there's a UDL, you'll see that there is a load UDL. And if you remember the relationship between UDL with shear force is 1 degree, so the UDL is 0 degree, a straight line, slope is 1 degree, so moment will be 2 degree, so it will be a curve of 2 degree, and it will be positive, negative, positive. Okay. And the maximum value will be where the shear force is equal to 0, wherever the shear force is equal to 0. That will be your maximum moment. Okay, so that's how we draw the bending moment diagram and shear force diagram for a indeterminate beam. Okay, and so that's how we solve all the indeterminate beam problem with no settlement using slope deflection equation. Okay, thank you.